Hello and all. So I'm just continuing this race condition here. When more than one process is executing the same code or accessing the same memory or any shared variable in that condition, there is a possibility of the output of or the value of that particular shared variable might be wrong. This situation is called as race condition, which I told in the previous video itself. That means there happened data inconsistency. That happening of data inconsistency is called as race condition. So several process access and process the manipulation over the same data concurrently. So at that time we need to follow a sequence, a particular order in which the access takes place. So the outcome is also depend on this particular order. So here comes the definition. It is actually a situation that may occur inside a critical section. Next comes the thing called as critical section, because in the heading itself we saw first we are going to give the introduction about process synchronization, and we are going to move out the critical section problem. So what is actually critical section? We already know the definition of process and what is the difference between a process and a program. Now the definition of critical section is nothing but each process will have its own segment code, which we are definitely calling it as critical section. So in which the processor may be changing common variables, or they can do any modification or updating a table or writing a file and so on. These things which will be happening in critical section here. What is the condition given for critical section is no two processes are executing in their critical sections at the same time. See, here is we have three sections in critical section. One is the entry section, exit section, and remainder section. What is happening in entry section is each process, while entering into the critical section, priorly it has to get the permission request from the critical section. Then only it can move to the entry section. The next is exit. Once the process entered into the entry section and all the work has been done, and next once the work is over, it has to move on to the exit section, and remaining code will be placed in the remainder section. So this is the general structure of the critical section here. So whatever may be the solution for the critical section problem, it has to satisfy the following three conditions. What are all the conditions? The first thing is called as mutual exclusion, the second is progress, and third is bounded waiting. If I take mutual exclusion, what is the definition in mutual exclusion is if process PA is executed in its critical section, no other process can enter into the critical section. Progress means if one process doesn't need to utilize the critical section, it has to allow the other process to get into the critical section. It should not stop. Bounded waiting, there exists a bound or limit how long a particular process can be inside the critical section. That should be also taken care. Request to enter its critical section, and before that request is granted. So see here, this is one example for the the left side diagram is called as critical section, where only one process can be entered. This scenario, right side scenario, is totally wrong, where all the four processes are inside the critical section, which condition is not possible. So what are all the approaches to handle a critical section? There are two general approaches. One is preemptive kernel and non-preemptive kernel. What is the meaning of preemption? Preemption, you already know. If one process is executing, there is an authority for one more process to enter. It can interrupt the running process that I need a chance to execute my program code also. That is called as preemption. Non-preemptive is which the thing which I have told, it won't be happen at any cost. So that is these are all the two approaches. So we will be seeing this Peterson solution in the next video. Thank you.